1 squared plus 2 squared plus k squared plus k plus 1 squared. Now, this is what the partial sum gives us. Then the formula, on the other hand, will give us, this is equal to k, bracket k plus 1, we are going to explore the use of mathematical induction in the proof of certain identities. On the board, we have a sum, 1 squared plus 2 squared plus 3 squared plus dot dot plus n squared, which is equal to n bracket n plus 1 bracket 2n plus 1 all over 6. Now we're going to use mathematical induction to prove that this identity holds when n is equals to 1. We're going to also prove when n is equals to 2. Then we're going to prove this same identity when n is equals to k, and then we now prove that it is true for n equals to k plus 1. Now we're going to use the notion of partial sum, and then we're going to use the notion of partial sum. Let the partial sum be this, n bracket n plus 1 to n plus 1 all over 6. Now, when n is equals to 1, we have S1 is 1 squared, which when we substitute into this formula, of course, 1 squared is equals to 1, but when we substitute into this formula, we're going to have 1 bracket 1 plus 1, bracket 2 times 1 plus 1, all over 6. That will give 1 times 2 times 3 all over 6, and that is 6 over 6, which is equals to 1. So when n is equals to 1, the partial sum on this side will give us 1 squared, which is equal to 1. And then the equation, the formula, when we substitute the value n equal to 1, will give us 1. So the left-hand side is equal to the right-hand side. So we have proved that this equation and the partial sum here is true when n is equals to 1. Now we're going to prove it for n equal to 2. If n is equals to 2, the partial sum will give us 1 squared plus 2 squared, which is 1 plus 4, and that is 5. Okay? Now, if we substitute this into this formula, we're going to have 2 bracket, when n is 2, we have 2 plus 1. We have 2 times 2 plus 1 all over 6, which is giving us 2 times 3 times 5 all over 6. That is 30 over 6, which is 5. So the partial sum on the left-hand side gives us 5 when n is 2, and then the equation on the right-hand side gives us 5 when n is equals to 2. So we have proved that this identity holds for n equal to 1. We have also proved that it holds for n equal to 2. Now we'll go ahead to prove by mathematical induction that it is also true for n equals to k. So what we are going to do now, when n is equal to k, we have the partial sum sk is equal to 1 squared plus 2 squared plus dot 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 plus k squared. Now that's what it gives us here. Now the formula will give us k bracket k plus 1 bracket 2k plus 1 all over 6. So it is true for n equal to k. So it is true for n equal to 1, it is true for n equal to 2, now it is true for n equal to k. Now we go ahead to prove that it is true for n equals to k plus 1. When n is equals to k plus 1, the partial sum is sk plus 1 is 1 squared plus 2 squared plus k squared plus k plus 1 squared. Now, this is what the partial sum gives us. Then the formula, on the other hand, will give us, this is equal to k bracket k plus 1 bracket 2k plus 1 all over 6. The simple thing we are going to do is, what we did here was just to add the k plus 1 term to the partial sum on the left-hand side. So we are going to add the same term we added to the left-hand side to the what? Right-hand side. And then we simplify. So I just add this to the what? I add it to the right-hand side. Then all I need to do is to simplify the right-hand side so that I'll get an expression that is true, that looks like this, which is true for k plus 1. So I'm going to have LCM of this is, LCM is 6. So using the LCM, we have 6 there. 6 divided 6 is 1. 1 times there, we have k bracket k plus 1 bracket 2k plus 1 plus 1 divided 6 is 6. 6 times that is 6 bracket k plus 1 all squared. So we go ahead to simplify the numerator, and that gives us k. We have something that is common here. K plus 1 is here and k plus 1 is here. So if I bring out k plus 1 outside the bracket, I'm going to be left with k bracket 2k plus 1. Then I'll have plus 6k plus 1 left in the bracket, all over what? 6. Now, I'm going to erase this side of the board. I'll erase this side of the board. I'll erase this side of the board so that we continue from here. Now, let's simplify what is inside the block brackets. We are going to have k plus 1 brackets 2k squared plus k, that is expanding k times 2k and k times 1 will give you this, then plus 6k plus 6, everything divided by 6. Now, if we simplify that further, we have k plus 1 brackets 2k squared plus 7k plus 6, all divided by what? 6. Now, let's look at it more closely. This is a quadratic expression. If I factorize this, I'm going to have k plus 1 bracket 2k squared plus 4k plus 3k plus 6 divided by 6. And that gives us here k plus 1. Now here we have, in block bracket, I have 2k brackets k plus 2. All right. Then here we have plus 3, which is common, k plus 2, all divided by 6. And if I simplify this further, I'm going to have k plus 1. Then from here we have k plus 2. And then we have 2k plus 3, all divided by what? 6. Now, this is what we have so far. Now, this is the expression we have for the right-hand side of the partial sum when n is equal to k plus 1. Now, we try to make it look like that. What we have in the original equation is k. In place of k, we have k plus 1, showing that it is true for k plus 1. Now, when we have k plus 1 here, we are meant to have k plus 1 in place of k. And then for this one, we are going to have k plus 1 plus 1. Okay? K plus 1 plus 1 in place of that one there. Okay? Then we have the next one is 2k, okay, plus 2 plus 1 in place of that one, all divided by 6. And then when you simplify further, you have k plus 1. You have k plus 1 plus 1. And then you have 2 bracket k plus 1 plus 1 all divided by 6, which shows that it is true for, that formula is true for n equals to k plus 1.